Hi, my name is Rick Edgman, and I'm visiting Uppsala University's Campus Gotland, the Division of Quality Sciences from Utah State University in the United States. At Utah State University, I serve as the research director for the Shingo Institute, which is one of the major international quality prizes that's awarded each year. And I also serve as professor of management in the John M. Huntsman School of Business. So today I'm going to talk to you about the final phase of Six Sigma's most commonly used algorithm called DMAIC, D-M-A-I-C, which stands for, as you can see on the slide, Define, Measure, Analyze, Improve, Control. In previous presentations, we've talked about define, measure, analyze, and improve, and today we get to the final stage, control, after which we close out the project and look for new ones to work on. So there are two algorithms that are extremely popular in Six Sigma. One is this one, DMAIC. We use DMAIC when we're trying to significantly improve or introduce significant innovation into an existing product, process, or system. The alternative algorithm is called DMADV, and it's used in what is referred to as Design for Six Sigma, where Design for Six Sigma is used to develop new products, new processes, new systems. For example, at GE and at 3M Corporation, all new products go through a Design for Six Sigma process, DMADV. Those are also, in general, Six Sigma companies in that they apply Six Sigma DMAIC to many of their existing products, processes, and systems, especially those that may need more significant improvement. So before we really launch into this final phase, let's make sure that we have a common understanding of Six Sigma. There are many definitions that we might look at, but this is the one that I use. And it's due to myself, but also to two Swedish colleagues with whom I've worked in the past. So I refer to Six Sigma as highly structured strategies for acquiring, assessing, and activating the voice of the customer or the enterprise, or even listening to the competition that we have, the competitors, and gathering intelligence from them. Now, we do that for a purpose. We do these things with the purpose of providing really superior products, systems, designs, processes that will really delight our customers, really satisfy our customers. Why do we do that? Well, ultimately we do that because we think that's going to provide a long-term or a sustainable competitive advantage for the organization itself. So what do we mean by acquiring, assessing, and activating the voice of the customer? So whenever we hear the voice of the customer or customer intelligence, for example, think of that as data. We need to listen very carefully to what's being said, the information that's out there, gather that intelligence. Let's call it data. And then we need to be able to understand the content of the data. So it isn't just acquiring that data, it's understanding the content, the value, the message. So that comes with assessing the data analysis in many cases. But in general, it's extracting the information content from data. After we have that, we still need to do something with it. So just because I can understand what you say to me doesn't mean that leads me to any sort of an action. Six Sigma is action-based. And so ultimately what we want to be able to do is take what we've learned from our assessment of the data and implement that or activate the voice of the customer, or the voice of the enterprise itself, if it's an internal project, or perhaps act on what we've learned from our competition even. So that's what we're trying to do with Six Sigma. In the final phase of DMAIC, control, our goal is to institutionalize the improvement and implement ongoing monitoring. Ongoing monitoring because the nature of most processes, most systems, is over time they tend toward entropy. That is, they tend to decay in their performance rather than toward increasing organization and better performance if left to themselves. Hence, we monitor to make sure that whatever it is that we've done continues to work in the way that it should work. So as part of that institutionalization of the improvement and implementation of ongoing monitoring, we develop, we document, and we implement an ongoing process for the monitoring itself. We standardize that process. We document the procedures that we're going to use in the monitoring, and then we develop and make sure that our response plan is visible. So if anything happens to degrade the performance of our new and improved process or our new and improved system or product, then we want to make sure that people know what to do and that they understand the signals that something is going wrong. In other words, develop and display your response plan. So the standard sorts of phases that you would go through, or steps, would be that we would validate measuring systems. Now, we've done that before in earlier stages of DMAIC, but previously we did that as applied to the customer CTQs, critical to quality characteristics of your process, of your product, of your system, of your service, from the perspective of the customer. If we're talking about some sort of a statistical formulation, we would usually call that Y, as in the letter Y, meaning that going back to your old mathematics background, you would say that that is a dependent variable. Okay, the customer's response, the customer's reaction, what the customer sees as important, what we deliver to them, is a dependent variable. It comes in response to things that we do internally in the organization. Those things that we do internally in the organization, we might call control variables. Now, there are some that are very important to delivering what the customer wants and needs. There are many that are much less important or even trivial. So those few that are very important, we usually call the vital few. And we call them the vital few X's, or the vital few control variables or influential variables. You would call them independent variables. The others that have far less influence, or that we have far less control over perhaps, are usually referred to as the trivial many. That is, their collective effect on the customer CTQ tends to be small. So where do we concentrate our efforts? On those vital few X's, the control variables. So now in this stage, in the control phase of DMAIC, we're worried about validating, or concerned with validating, the measuring systems for those control variables, for those X's, those things that we internally control, that ultimately lead to improved outcomes for our customers. We need to validate the long-term capability of our new and improved process, system, or product. Okay. So in the past we've done that, but we've done that not with respect necessarily to the control variables. Now we're going to be doing those things with respect to the control variables. And then we implement our process control plan so that we can ensure that in the long term we don't have recurrence of whatever problems we've experienced in the past. Or if we experience recurrence, it is at a far lower rate, or a far lower frequency, or far lower severity when it does occur. So in control, what are we doing? We are controlling process performance and ensuring that the defects that we've identified in the past don't recur, the ones that we've worked on. So once defects have been reduced, one of the things that we need to know is how is it that we ensure that the improvement that we implement is sustained? So that is the first common question that we have in the control phase. Other common questions include what systems need to be in place to check that the improved procedures stay implemented. And how can those improvements be shared with the rest of the company? So Six Sigma is resource intensive. Companies don't use Six Sigma for everything. They use Six Sigma for important areas where it is truly important to achieve substantial improvement. That's where Six Sigma is more likely to be used. It's resource intensive in terms of people and other resources. And because of that, we don't use Six Sigma on everything. We save it for the so-called big stuff. Okay? And if it's for big stuff, whatever lessons we learned are lessons usually worth sharing with the rest of the company so that they don't have to relearn those same things on their own. We find a way to archive and share the information. So during the control phase, what we're trying to do is come up with a standardized set of documents for whatever procedures we implement, as well as a means to record data and to check it against historical values. So if we go back to the improve phase, define, measure, analyze, improve, and now we're in control. But if we reflect back on the improve phase, the goal there was to test and identify important sources of variation in the customer CTQ. Those important sources of variation, internally controllable, as we spoke of just a moment ago, are those things that ultimately become our control variables. They are the controllable X's, the independent variables that lead to improved customer performance. So improvements in Y, in the CTQ, the critical to quality characteristics as seen from the customer perspective. So those important sources of variation, those important variables, things that we control, maybe temperature, humidity, pressure, volume, the quality of the leather that we use in some product, the speed of the processor that we have in some instrument, and so on. Those things that we control become the control variables. Those are the things we're concerned about now in the control phase. So what we will want to do as steps in the control phase, steps 10, 11, and 12, would be to validate the measurement system for the control variables, to determine the process capability, and to implement the process control system and bring the project itself to a close. On this slide it says bring the process to a close. It's actually intended to say bring the project to a close. So as part of step 10, if you've seen the prior presentations on earlier steps in DMAIC, this should look familiar because previously we've done these same things but applied to the Y's. Now we're applying it to the X's, the control variables. So step 10 is to validate the measurement system of the control variables. So I say step 10, 11, and 12 in the control phase because a lot of times you'll see 3 steps listed for each of define, measure, analyze, improve, and control. Now the measure, analyze, improve, and control are the real guts, the real heart of the Six Sigma project. The first part, definition, we usually just list those steps as ABC. And then for measure, we have steps 1, 2, 3. For analyze, we have 4, 5, 6. For improve, 7, 8, 9. And now we're to steps 10, 11, 12 in the control phase. And all of those steps, ABC and 1 through 9, will have been covered in prior presentations on D, M, A, and I, define, measure, analyze, and improve. So now we're on steps 10 through 12. Step 10, validate the measurement system of the control variables. So you will see then that we establish a control system and the steps are precisely what you've seen before, but previously with respect to the Y's, previously with respect to the old system, so to speak, because we've implemented improvements. We now have a fundamentally different process or system. So we create an implementation plan with controls for each X, each of those variables that are internally controllable that we want to exercise strict control over to make sure that they continue to influence the customer CTQ in the way intended. That's A. B is prepare documentation and provide training as necessary. And C would be to collect data and reevaluate the process capability. I say reevaluate because you evaluated the capability of the process in its prior incarnation, the one that wasn't good enough. But now you've changed the process. It should be improved, and its capability, its ability to meet customer demands, to fulfill customer needs and wants, should be improved. Hence, the capability should be better than it was in the past. And then there are some suggestions as to how you might go about that. Step 11, determine the process capability. So now what are we doing? We are looking at the capability of the process in its new and improved form. We do exactly the sorts of things that we've done before. Things that might be worthwhile from a tool perspective at this stage would be particular types of capability indices that we've discussed in prior presentations, most notably probably one called CPK. And we want CPK, generally speaking, to be at least 1.33. So you might refer back to prior presentations to see what CPK is if you're not familiar with that particular capability index. Other tools that might be helpful would be a hypothesis test. A hypothesis test to see if in fact the customer response, the CTQ, is truly statistically improved to a level that makes a practical difference in their satisfaction, a practical difference possibly in financial performance for us the organization, and so on. And then step 12, implement process control systems. And there are different things that you might do depending on the circumstance, depending on your familiarity with different approaches to implement that process control system and bring your project to a close. One would be something like risk management. It is very similar to FMEA, failure modes and effects analysis, but now it is failure modes and effects analysis as focused on the X's, on those control variables instead of on Y, the customer CTQ. Because remember, we're trying to maintain control or exercise control over the process that leads to the CTQ now, hence over the x's, the control variables. So in the same way or in a similar way that we talked about failure modes and effects analysis related to the CTQs, now we would talk about something very similar to failure modes and effects analysis, but for the control variables. Okay, and we would identify a risk assessment plan. That would be the risk management, and we would identify measures or steps that we would take if in fact there are any breaches in the control that we exercise. You might use something called mistake proofing. In the Japanese, we would call that poka-yoke. So I'm affiliated with the Shingo Institute at Utah State University, and the Shingo Institute is named after Japanese quality master Shigeo Shingo. Dr. Shingo is perhaps the person, or was perhaps the person, given the greatest credit for the development of the famed, the world-renowned Toyota production system, now used by so many companies. We know it maybe as the Toyota production system. You may know it as lean enterprise approaches or lean manufacturing. So, poka-yoke, okay, mistake proofing. The idea behind mistake proofing is to make it essentially impossible to make a mistake, and that if a mistake is made, that it is detected immediately so that it can be corrected quickly. And then one of the last things discussed in prior presentations, but that we might revisit just briefly, would be statistical control charts. They've been in use in their most rudimentary form since the 1920s, as developed by Walter Schuchart, with many refinements and new types of control charts developed in the interim period of time. So you might recall that a typical control chart might look something more or less like this. I have the lines in color just to assist you in your ability to go through this. So what you have would be two red lines. Those red lines are positioned at 3 standard deviations away from the center line, the center line being the center green line. The yellow line is positioned at 2 standard deviations away from the center green line. So a standard deviation is the standard deviation of whatever performance metric that you're examining. And then the green lines, the outer green lines, are positioned at 1 standard deviation away. We look for patterns as the data emerges from the process. So when Schuchart developed the initial chart, it was just 1 point outside of the red lines. If the most recent point was outside of the red lines, you went to your supervisor and asked them to take action, which might mean shutting down the production line, for example. But rather than wait for something like that, which is akin to having the building already on fire, we would like to have some early detection sorts of capability. And so different patterns were developed that allowed us to have early detection capability. All of the patterns that we might look for in a control chart share 2 common traits. One of those traits is that if nothing has changed in the process, then having that pattern occur would be a very rare thing. Could potentially happen just by chance, but highly unlikely. So what does that mean? Highly unlikely means somewhere between about a 1 in 250 and a 1 in 1,000 chance of just occurring by chance if there's been no change in the process. So that if you see one of those patterns, and listen to my emphasis here, if you see one of those patterns, then there is a very small chance that nothing's changed. Could happen, but it's a very small chance, 1 in 250 to 1 in 1,000. It is an almost certain chance, somewhere between 249 out of 250 or 999 out of 1,000. That something has caused that pattern. And it is up to you to find that cause. There is an assignable, identifiable cause for that pattern. It's up to you as the process expert, or up to a team familiar with it, to identify the cause and to see what's going wrong. And of course, in the control phase, these are applied to the X's, the control variables. So there were different pattern analysis tests, 4 that are used on any type of chart. Pattern 1 was the pattern that Dr. Schuchart used, of having 1 point plot be on zone A. That is 1 point that's at least 3 standard deviations away from the mean, whether it's above the upper red line or below the lower red line. That ordinarily indicates a large and abrupt shift in process performance, in the process average performance level. Pattern 2 is a very subtle change in the average performance level. How subtle a pattern is, you can tell by looking at the number of points it takes to detect the pattern. The more points, the more subtle the change. So when you're looking at a pattern that requires 9 points, the 9 most recent points that you observe to be examined, that tells you that it's a very subtle change. This would say that we have either all 9 of those points above the middle green line, the center line, which is positioned at the average performance level of whatever it is you're monitoring, or alternatively that all 9 of those points are below that center line. And the chance of that happening, just by chance, is in the vicinity of 1 in 250. So if you see it, whether it's on above, all 9 points above the center green line or all 9 points below the center green line, that's usually an indication of a small shift in the mean. An increase if those points are all above the center green line, a decrease if they're below the center green line. Pattern 3, 6 consecutive points that are rising or 6 consecutive points that are falling. So when you have that, that is usually a gradual but ongoing change in the mean. If they're rising, then the mean performance level is going up. That could be good, could be bad. It depends on the context of the problem, of course. If all 6 points are going down, then the average performance level is decreasing, or the average mean. Maybe I should put it that way. The mean performance level is going down. Could be good, could be bad. If you're trying to do something faster and you're seeing a drop in the amount of time it takes to do something, that could be a good thing. Okay. So generally speaking, these patterns all by themselves are neither good nor bad, generally speaking. Whether they're good or bad depends entirely on the context. What they are indicators to you that something has changed in the historic process performance. Pattern 4 would be 14 points alternating up, down, up, down, up, down, up, down. If you see that pattern, it's typical that one of two reasons exist. One reason might be that the points that are all up reflect data that's coming, let's say, from one source, and the points that are all down are data from another source. You may intend, you may hope, you may believe that those two sources are producing identical data. But what the chart would be telling you is, no, they're not. So for example, you might be having information or output from machine A, be the up points, and from machine B, be the down points. Or the up points be coming from work that comes from the first shift of the day, and the down points from the second shift of the day, or something of that sort. So the solution for you in that instance would be that you actually need 2 charts, at least in the short run. You need 2 charts. One for machine A, one for machine B. One for shift 1, one for the second shift. Okay? Because they're not identical processes, at least for the present. In the future, perhaps you bring them into alignment and you can use 1 chart. But in the short run, no. The other common cause of that sort of pattern is over-interference by somebody involved with the process. So what I mean by that, for example, is let's suppose that the first point is too small, well below the center green line. So the well-intentioned person operating that process, or in charge of that process, makes some adjustments that they think will bring up the performance level. It does. Too big now. So they adjust. Too small. Too big. Too small. Too big. Too small. Too big. Too small. Over-interference in the process. Process variation is natural. There is a natural amount of variation in the output of any process. So what you're looking at is, in fact, that you have over-interference by someone, and the result is that you actually have increased variation because that person has inserted themselves into the process with good intentions, but nevertheless producing additional variation in the output. So patterns 1 through 4 can be applied to any type of control chart, and there are many types. Patterns 5, 6, 7, and 8 are, ordinarily speaking, only applied to the X-bar chart, the one that monitors the process mean, where you're measuring quantitative data. On the other hand, a knowledgeable statistician would be able to tell you that there are places where you can adapt and use patterns 5 through 8 to other charts. So patterns 5 and 6 deal with changes in the average performance level. Now remember, pattern 1 was a large, abrupt, sudden change in the average performance level. Pattern 2, which was 9 consecutive points either above the center green line or 9 consecutive points below the center green line. Pattern 2 was about detecting a subtle change in the mean. Pattern 3, 6 points rising or falling, a gradual but ongoing shift. Pattern 4, very different. But 5 and 6 are talking about intermediate changes in the average performance level. So pattern 5 is closer to pattern 1. It only requires 3 points. All 3 points, the 3 most recent points that you're looking at, have to be above the center line, or all 3 have to be below the center line. And 2 of the 3, or even all 3 of the points, need to be at least 2 standard deviations away. That means they need to be at least as far out as the yellow line. Okay, so at least as far out as the yellow line. That's a very rare pattern. Given that it only takes 3 points to detect this pattern, that should tell you that this indicates a pretty large shift in the mean, in the average performance level. Not as extreme as pattern 1, but much more extreme than pattern 2. Pattern 6 also is about a change in the average performance level for the process, but it requires 5 points, so it's a change that is a little more subtle than that of pattern 5 that we just looked at, but not as subtle, not as small as the pattern that you detect with, or the change that you detect with pattern number 2. Okay, so 5 points, the 5 most recent points, all on the same side of the center line, so either all above the center green line or all below the center green line. But of those 5 points, at least 4 of them, potentially all 5, need to be, let's say, beyond the outer green line on that side of the center. Okay, so at least 4 of the 5 points, potentially all 5, have to be at least 1 standard deviation away. Rare pattern, but a subtle change. Okay, a subtle change. Either a relatively subtle increase in the average performance level if we're talking about being above the center green line, or a decrease if we're below the center green line. Patterns 7 and 8 are entirely different. Patterns 7 and 8 are about detecting changes in the variation of the process. One of them is, generally speaking, a good pattern, at least assuming that all your calculations are correct. And since your calculations are probably being automated by software, that usually should not be a problem. But pattern 7 will almost always be a good pattern, one hard fought to get to, hard won, that comes from incredible effort aimed at decreasing process variation, whereas pattern 8 will be an indication that you have had an increase, an undesirable increase in variation, and it is like the 5-alarm fire. You need to do something about it if you detect pattern 8. So pattern 7, let's see what we've got. Pattern 7 says 15 consecutive points plot in zone C spanning both sides of the mean. What that means is that you have 15 consecutive points, your 15 most recent points, let's say, and they are all inside the green lines. Okay, all inside the green lines. Some above the center, some below the center, but all within the green lines. That's very, very, very unusual. So that if we see that, that says, wow, we expect a number of those points. We expect maybe 2/3 of those points to be inside the green lines, but not all of them. Maybe 2/3, but not all of them. Okay, so this is a rare pattern that indicates decreased variation, typically coming from the actions that you've implemented with that intention of decreasing variation. Pattern 8, the opposite. It only examines the most recent 8 points. It only needs the most recent 8 points. But none of them are inside the green lines. All of them are outside. All of them are at least 1 standard deviation away from the mean, or from the average performance level, that center green line, some bigger, some smaller. Okay, that usually indicates that process variation has increased, and that is almost always a negative indication. So you'll want to identify that problem and take care of it as quickly as possible. So remember, we've been dealing with the definition for Six Sigma, what it's about. In this particular presentation, only about the control phase, but in general, that Six Sigma is about acquiring, assessing, and activating customer, competitor, and enterprise intelligence for the purpose of producing really superior designs or innovations in our process, products, and systems. We do that with the purpose of serving our customer dramatically better, and in serving our customer dramatically better, of creating a sustainable competitive advantage for ourselves. So I hope that that this has satisfied some of your needs about learning about Six Sigma. There is so much more to the field, and this is just the beginning of an overview. The nuts, the bolts, all of the tools, the techniques, and more of the strategy require deeper study. Thank you very much.